Okay, so this question, we are provided a gaseous equilibrium reaction. We are provided initial concentrations, and we're asked to calculate equilibrium concentrations. So we first calculate Q to determine which direction the reaction will proceed. We use that to set up the ICE table. We calculated Q to be less than K, which means reaction will proceed to the right. We're going to use up reactant and produce product. So we have negative X for reactant, positive X for product. And our goal is to calculate equilibrium partial pressures, but we don't have any equilibrium partial pressure, so we can't calculate X directly. We had to create these factors, which is initial plus change for equilibrium partial pressure, and then plug that into the K equation, or the K expression, setting that equal to 32. That was a provided value at the top of the slide there. So after this, everything that we did on this slide and the next slide was simplifying this expression. So we added the factors into here, multiplied the top, multiplied the bottom, combined the like terms, and then arranged into an ax squared plus bx plus c format equal to 0. Because once you're in that format, you can solve for x using the quadratic formula. So then we plugged into the quadratic formula. This is where I have an error. 2 times 127 is 254, not 224. And so the two options for x values are 0.719 and 1.04. So these are only different because I had the wrong number here. So with the quadratic formula, you always get 2 different options for x, because we have 226 plus 40.9 divided by 254, or 226 minus 40.9 divided by 254. So we have 2 options for x, and we need to look back to the ICE table and think about which one of these would make sense, would apply. We're going to look at this one first. The 1.04. Let's say x is equal to 1.04. Going back to the ICE table, if we had x as 1.04 here, then 2x would be 2.08. Equilibrium would be 1.75 minus 2.08, and that would result in a negative pressure for the RCL, which won't happen. So whichever one gives you the negative pressure for any, that's not the x value that you use the other one. So you could always plug both in, both options for x, and then use whichever one does not give you a negative value. So we are using this one here, x equals 0.719, because this one results in negative partial pressure of BRCL at equilibrium. If a substance is present, it will not have a negative partial pressure. It should have positive. All right, so we did all of this to find the x value. Now we plug that into those equilibrium factors to find equilibrium partial pressures for each component. So we're almost done with this question. We just need to do this final calculation to answer the question, which is, what's the partial pressure of each component at equilibrium? For BRCL, going back to the ICE table, equilibrium partial pressure is equal to 1.75 minus 2x. So now we know the x value, we're just plugging that into that expression. Partial pressure of Vr2 at equilibrium, 0.750 minus x, which is 0.719, or plus x, I'm sorry. And then partial pressure of Cl2 at equilibrium is 1.15 plus x. Partial pressures are in units of ATM. So when we calculate our final pressure, for each one, we have ATM units. And then this is our final answer here. So all of these steps that we did were needed to calculate equilibrium partial pressures of each component present. So again, we started with Q, set up the ice table, use the provided K value to solve for X, and then replug X back in. Yeah.
If a question like this was on the exam, would the quadratic formula be
Yeah, it would. Yeah. Other questions on this? Nothing? Ready to move on? Get away from these calculations? I see some of you are still writing, so I'll wait one moment and then we'll go to the next section. Okay. So next section is much more qualitative, meaning we won't be doing these extensive calculations. We'll be thinking conceptually about how equilibrium will change with response to different pressures or different stresses is what we'll call them. So we'll identify reaction conditions that shift equilibrium position of a reaction. So first let's remember what is constant at equilibrium. Well, we know we have constant concentration of reactants. We have constant concentration of products. We also have constant temperature. The previous example that we did, it was at 500 Kelvin. We've brushed over the temperatures because we're assuming that they stay constant, but the temperature information has been provided in a couple of examples. But if temperature is changed, that impacts equilibrium. So we'll explain and talk through why that is. Other things that remain constant are volume and pressure. Volume and pressure are mostly relevant for gaseous equilibrium reactions, less relevant for aqueous. But all of these factors are assumed to be constant when a system is at equilibrium, and if any of these factors are altered when that system is at equilibrium, we say that a stress has been applied to the system and it is no longer at equilibrium. But remember that reactions always tend toward equilibrium. That's the lowest energy state. Everything's looking to be at lower energy when we're talking about chemistry. So if a system's no longer at equilibrium, it will shift in a way to reestablish equilibrium. So Le Chatelier's principle, which is what the section is about, states that if a stress is applied to a system at equilibrium, the reaction will tend to shift in a direction. By direction, I mean shift to the right to produce more products or shift to the left to produce more reactants. But it will shift in a direction to relieve that stress. So using this principle, we can qualitatively predict how stress will affect a system. Qualitative meaning we're not doing calculations. So we're not going to calculate exactly how much more product is produced, but we'll just say more product will be produced, or vice versa, if reactants are increasing in concentration. We're going to start with talking about changes in concentrations, which we've really already talked about when we talked about Q. But now we're going to say the system is at equilibrium. So we just have generic reactant A and product B. That is at equilibrium. And then the first bullet point, let's say you can add more B to the system. So the system's at equilibrium, you have B in a beaker and you add more B. You add more product. You're increasing the concentration of product, which means that Q at that moment, which is concentration of product over reactant. You add more B, concentration of product has now increased, so the reaction will shift to the left to reestablish equilibrium, to then produce more reactant so that the product to reactant ratio will be equal to K. So increasing something on the left side will cause the reaction to shift right. Or I'm sorry, I said that backwards. Increasing something on the right side will cause the reaction to shift left. Let's say you have A and B at equilibrium, and you're able to remove B from that system. So the concentration of B is decreasing. That would result in a Q that's less than K, so the reaction will shift to the right to produce more B, to reestablish equilibrium. B is removed. We need more B then to be at equilibrium, so the reaction shifts to the right. So that's all that we can do on the right side. We can add products or we can remove products. We can do the same thing on the left side. If you add reactants, so you have A and B at equilibrium, you have another vial of A, and you add more A to that system. We've increased the concentration of reactants. There are more reactants to react. The equilibrium will shift to the right. To produce more product. And then, if we have some method to remove A from that system at equilibrium, we decrease the concentration of A, which was the reactant. That would make Q greater than K. The reaction will shift to the left to produce more reactant. So in all of these scenarios, the reaction shifts to reestablish equilibrium. In the last one we talked about, if we decrease reactant, then the reaction will shift to produce more reactant to accommodate that initial decrease. So that means the reaction shifts to the left to produce more reactant. Okay, let's do this question. So we have a system here, H2S in equilibrium with H2 and S2. We're saying that this system is at equilibrium. Which direction will the reaction shift if more H2S is added? Then assume the system reaches equilibrium again and H2 is added, so which direction will it shift? Then it reestablishes equilibrium and S2 is added. So 3 independent questions, assuming the system's at equilibrium as you are answering each one. Yeah. Okay. So like which will start to be products that they should like on the right side of the product, it's like a produce more product to accommodate for change.
Just quick question. This is additional HTS, so right? So you need two, right? So- If you look.
It will, yes, but I think it's maybe more straightforward to think of like H2S is added, so is that a reaction process? Right. Yes, so we've added more reactant to the system, so now what will happen is shift to the left means producing more. But we already added more. Yeah, so now with more reactants there, it will start producing.
Next one is shift to. And this one would be.
Wait, hold on.
This is.
Yeah.
I'm tripping.
One more minute, and then I'll close it.
So it's added to the system. So it means it needs to go to the right. Then that's added to the system. So it needs to go to the left. And then it needs to go to the right. So that also means it needs to go to the left. That's what I'm saying. Okay, fine. Okay, that's number. Bro.
All right, I'm gonna close it here. Okay, so we have a system at equilibrium. If additional H2S is added to the system, H2S is a reactant. So if we increase concentration of a reactant, there are more reactants that will react and produce products. So the reaction will accommodate that shift, or it will accommodate that change, increasing starting material or increasing reactant concentration by using up that reactant and producing more product. We're trying to have Q equal to K. K does not change, but Q can change. So if we've increased H2S, increased reactant, for that ratio to remain the same as K, then product should be increased. So it shifts right. Second question, additional H2 is added. So now we're adding more product. Adding stuff on the right side will cause a reaction to shift left. We have more product there that will react, and that means that more reactant, the reverse reaction will proceed, and this will shift left. And then the last one, if we are removing S2 from the system, then we're decreasing product concentration. To accommodate the decrease in product concentration, the system will shift to produce more product. So reestablishing equilibrium, if we've got less product present, then the reaction shifts to the right to produce more of that product. So this one shifts right. So again, the goal is to reestablish equilibrium. If we increase something on the left, the reaction will use that up. If we increase something on the right, the reaction will use that up and proceed left. Or if we decrease, then the reaction will reproduce whatever is decreased. Questions on this here? Okay, so we'll talk about now altering volume. So this is relevant for gaseous reactions. So reactions that are in the gas phase. So according to the ideal gas law, pressure and volume are inversely proportional. If you increase pressure, like starting here and then adding pressure, you're decreasing the volume. So that's what these next two bullet points say. As pressure increases, volume decreases. Or if volume is increasing, pressure is decreasing. Or pressure decreases, volume increases, vice versa. So what this means, for a reaction, a gaseous system that is at equilibrium, reducing container volume will increase the total pressure. So if we've decreased volume from here to here, we've increased pressure of that gas within the system. We have more moles of gas per volume. Or same moles of gas, but lower volume. So what happens when pressure increases or volume decreases, they're interchangeable in this scenario. The reaction will shift towards the side with fewer moles of gas. To offset decrease in volume. So in this image here, we have this gaseous equilibrium reaction. 2 moles of NO2 form 1 mole of N2O4. So at a large volume, we're assuming this is at equilibrium. We have 4 moles of O2 and 1 mole of N2O4. At equilibrium, that's 5 total moles of gas. We decrease the volume, or we could say we increase the pressure. The system is not at equilibrium currently. It reestablishes equilibrium by now forming more moles of N2O4, which overall decreases the total moles of gas in the solution. So now with a different volume, a different pressure, K has a different value. Changing pressure will change the K value. At equilibrium, we now have more product than equilibrium with less pressure or larger volume. So with change in pressure or volume, because if one changes, the other one will also change. The K value changes. So at equilibrium, K will have a different value because we now have a different relative concentration of products to reactants. But the main message here is that if you decrease volume or increase pressure, then the reaction tends toward the side with fewer moles of gas. By moles of gas, we're looking at coefficients. So left side has 2, right side has 1. Increasing pressure, we tend toward the right side. So now at equilibrium with higher pressure, there's more product than reactant present. The second bullet point is the opposite scenario. So for a gaseous system at equilibrium, if you increase the container volume, that decreases the total pressure. And the reaction will shift towards the side with more moles of gas. To offset the increase in volume. So when you're ready, go to the next slide. We have two reactions. For those two reactions, describe how each will shift with a decrease in volume. Will they shift to the left, right, or neither? All right, for our first reaction, how many moles of gas on the reactant side? 2 moles. So we have 1 mole of H2 and 1 mole of Cl2. So we have 2 moles of gas on the left side. On the right side, we have 2 moles of HCl. So 2 moles on the left, 2 moles on the right. Volume is decreased. The reaction tends toward the side with lower number of moles. But in this case, there is no side with lower number of moles. So decreasing the volume will not shift the equilibrium. So this one has no change. So we got the same number of moles on both sides, so no change. Second reaction, 1 mole of nitrogen, 3 moles of hydrogen, that's 4 moles on the reactant side. And then 2 moles of NH3, 2 moles on the product side. So when the volume is decreased, reaction shifts toward the side with fewer moles, so this shifts right. All right, ready for our next condition? Okay, so we talked about changing concentrations, changing volume and pressure for the slide in the previous one. Now we're going to talk about how changing temperature, this also causes the K value to change for a given reaction. But to know how K changes, we need to know if the reaction is exothermic or endothermic. So the sign of the enthalpy, delta H, tells us how K will be affected by a change in temperature. So remember, endothermic reactions have delta H greater than 0. Energy is required for endothermic reactions overall. Exothermic reactions, delta H is less than 0, so it's a negative sign. Exothermic reactions overall release energy. So for an endothermic reaction that requires energy, remember, increasing temperature or adding heat is increasing the kinetic energy of the substance. So adding temperature or increasing temperature or adding heat is increasing the energy. So if you're adding energy to a system that requires energy to produce products, it's like adding a reactant. You're adding more of what's required for the reaction to proceed. So with a temperature increase for an endothermic reaction, the reaction K value, well, the reaction overall will produce more products because it has more energy to do so. So that means the K will increase. So with an endothermic reaction at equilibrium, and you increase the temperature, that system's no longer at equilibrium. The equilibrium will have a higher product concentration, and that's what we mean by K increases. But at that time that you initially add increased temperature, that system's no longer at equilibrium, so we are not describing K of that system. We can describe Q. That system's not at equilibrium when you first increase temperature, but since K has increased for that reaction with the increase in temperature, that means Q at that time is less than K, and so the reaction shifts to the right. The next 2 slides will discuss endothermic for one slide and exothermic in another slide in a little bit more detail. But this table will summarize everything. So endothermic, where energy is required, if you add energy, reaction shifts to the right because K increases. At equilibrium, you'll have higher concentration of products. Now, as you can probably imagine, if we decrease temperature, the opposite will be true. So energy required, we're removing energy. That means fewer products can be generated or will be generated at equilibrium. So K will decrease. So Q at that time will be greater than K, and the reaction will shift to the left. Okay. For an exothermic reaction, we see the opposite for the same change in temperature. Exothermic reactions release energy overall. So energy is kind of like a product. It's being produced by the reaction. So if you add more energy by increasing temperature, that's going to prevent the forward reaction producing products, and it will cause the reverse reaction to occur and produce more reactants. So K decreases. With K decreasing, Q will be greater than K, and the reaction will shift to the left. Then for an exothermic reaction where we're decreasing temperature. So imagine a reaction that produces heat. If you add it to a flask and you feel the outside of the flask that's hot. You then put the flask into an ice bath, you're removing energy from that system. From an exothermic reaction, that's like removing a product that will cause the reaction to produce more product. So K increases, increasing concentration of product. And so the reaction will shift to the right. Okay, next slide has just a little bit more details about endothermic reactions. So endothermic reactions overall require heat. We can treat heat as a reactant. So adding heat will follow the same process as if we're increasing concentration of a reactant. Increase something on the left side causes the reaction to shift to the right. So adding heat causes the reaction to shift right. There's a typo on this slide and the next slide. The last line, removing heat causes the reaction to the left. But remember, when we're talking about temperature change, we need to have information about the enthalpy. If you don't know if the enthalpy sign is positive or negative, then you can't answer these questions. We have to know if the reaction absorbs energy or releases energy. So this slide, endothermic requires energy, absorbs energy. Next slide, exothermic. Heat is released or heat is produced, so we can treat heat as a product or energy as a product. So adding heat, we're adding a product, quote unquote product, that will cause the reaction to shift left. Removing heat is like removing a product, causes the reaction to shift right. Okay, so let's go to this next slide. We have an endothermic reaction. So that tells us this reaction requires energy, absorbs energy overall. First question, how is K for the reaction affected by an increase in temperature? Does K increase or decrease or stays the same? Then what direction will the system shift after this change in K? And then how will the partial pressures of each gas in the reaction be affected by that shift? So I'll give you all a few minutes to work on this. I'll go back in case you were still writing. Will that cause, like, will that partial pressure, will that increase or decrease the reaction? Okay, so what happens to so this hydrogen decreases. Yeah, and more hydrogen. So that concentration of it there.
Yes, I said.
All right, we have an endothermic reaction. Energy required or overall is absorbed by the reaction. So if we're adding energy by increasing temperature, what happens to K? What is it, Lavin? It increases. Why does it increase? Yes, that's true, but why is that true? What causes K to increase? What else has to increase? Products, yeah. So if we have an endothermic reaction that requires energy to form products, we add more energy and more products will be formed, which means K will increase. So K increases. So if K increases, then how will the reaction shift to accommodate that equilibrium change? To the right, yeah. So we'll have more products at equilibrium. The reaction needs to produce more products to reach equilibrium. And so what does that mean for the partial pressure of NH3? Does that change? It what? Sorry, I can't tell if you're saying increasing or decreasing. Okay, so yes, so we have the reaction shifting to the right, which means we'll have less reactant present at equilibrium. So if there's less NH3 present, then the partial pressure will decrease. But we have more hydrogen and nitrogen at equilibrium, so the pressures of those two will increase. Increasing concentration means we'll have an increased pressure, partial pressure. Okay, so we discussed changing concentration of reactant or product will not change the K value, but it will cause a reaction to shift in a direction to reestablish equilibrium. Then we said if we change volume or pressure, that is important for gaseous equilibrium systems, where if you decrease volume, the reaction shifts towards the side with fewer moles of gas, and vice versa. And then temperature depends on if you have endothermic or exothermic, it will shift K. One more to discuss is adding a catalyst, which really is no effect. So remember that adding a catalyst increases the rate of the reaction by lowering the activation energy. This is an image that we saw. This is an uncatalyzed transition state energy, really high activation energy. This is catalyzed, much lower activation energy. But the presence of the catalyst doesn't affect equilibrium, because at equilibrium, you'll still have the same concentration of reactants and products. So we say the catalyst doesn't affect equilibrium position, but the other factors that we discussed will. Okay, we will end there. So we'll start chapter 16 on Friday. Yes.
Remember how I asked you if on the ice table, like the first time we did it, like the products and reactants add up together?
Yeah. Has that been the
So
case?
I did it again for this one. They did.
You
They
did?
both did on two sides. So
Okay.
I think it is true.
Okay, interesting. That's good to know. Thanks. Yes. Oh, let me just stop the recording real quick.